Usually when we talk about writing code, there's this expectation of absolute control, right? You write a function, you pass it an input, and you get exactly one output back.
Yeah, it's very predictable.
Right, it's like a vending machine. You walk up, you press B4, the coil turns, and you get your candy bar.
Yeah,
You know the exact sequence of events from the moment your finger hits the button.
exactly. I mean, traditional software engineering is built entirely around that comfort. It's highly linear.
But then, you step into the world of autonomous AI and agentic workflows, and suddenly that vending machine is staring back at you.
Yeah, and it's asking for a credit card.
Right. It's checking the local weather, realizing you're shivering, and deciding it actually wants to bake you a hot pie instead. It's wild. We're looking at an architectural landscape that is, well, incredibly dynamic.
It really is. You aren't just scripting a strict path anymore. You're orchestrating an environment where a model makes autonomous decisions.
And welcome to a very special deep dive. Today, we are entirely focused on you, our listener. We've got a massive stack of architectural blueprints and certification documentation spread out in front of us.
We really do.
Our mission for this deep dive is to prep you for your Claude architectural certification. Specifically, we're tackling Domain 1, which is agentic loops and the core API.
Yeah, and we're adopting the persona of your expert certification tutors today. Just imagine we're sitting right across the table from you.
Exactly.
If you could see our setup right now, the backdrop for today's session is essentially a digital command center. I mean, we are surrounded by flowing code, architectural diagrams, message state traces.
It looks like the Matrix in here.
It really does, but it's the perfect environment to really lock in these concepts. We're treating you as a pure architect who just needs to formalize this knowledge.
Yeah, we are going to master the mechanics of how Claude agents actually execute. We'll look at how they think, how they request to use tools, and how they loop back into the conversation to keep working until a multi-step task is truly done.
Because that's what the exam tests.
Right, and I promise you, by the end of this deep dive, you're going to be absolutely bulletproof on this exam. Okay, let's unpack this.
Let's do it.
We throw the word loop around a lot. But in this specific architectural context, what makes an agentic loop different from just like a standard while loop in Python?
Well, at its core, an agentic loop is a controlled autonomous execution cycle. It's the mechanism where your application calls Claude, Claude evaluates the problem and maybe realizes it lacks information.
Okay.
So it requests tools. Your application then pauses, goes out and executes those tools in the real world, appends the fresh data back into the conversation history, and then loops back.
It just feeds it right back in.
Exactly. It iterates. Unlike a simple, single-turn chat interaction, an agentic loop allows the model to reason across multiple distinct steps. It grounds its logic in external data before ever returning a final answer.
It's like the difference between asking for a static fact and asking an assistant to go do comprehensive research for you across 4 different databases.
Right, exactly.
But here's the architectural challenge, right?
Yeah.
If this thing is leaping on its own, fetching data, thinking, fetching more data, how does the calling application actually know when to keep looping and when to finally stop?
And that brings us to the most critical concept you will face in this entire domain. We call it the golden rule of control flow.
The golden rule, I like.
Yeah. There is exactly one authoritative signal for loop control, and it's a specific field returned on every single API response. It's called stop reason.
Wait, so just stop reason, not the text content of the response, not counting how many times the loop has run.
No, just that one field. I mean, stop reason is an immediate top-level variable. It is a version-stable ground truth emitted directly by the inference engine itself.
Oh, wow.
Yeah, often before the actual response content is even fully serialized. It's not derived from analyzing what the model is saying. The certification exam will absolutely try to trick you into checking other things.
So don't fall for it.
Don't fall for it. Stop reason is your only loop controller.
Okay, so it's basically a traffic light at an intersection. You don't guess if you should drive forward by looking at the types of cars around you, right?
Right, that would be dangerous.
Or trying to read the bumper stickers on the car ahead of you, which in this analogy would represent the text content blocks.
That analogy holds up perfectly, actually.
You just look up at the traffic light. The stop reason tells you exactly what to do, devoid of any other conversational context.
Exactly, and there are 3 main states you need to memorize for that traffic light. The first is too loose.
Okay, too loose.
This is your green light. It means Claude wants to call one or more tools, so your action is to continue the loop. You execute the requested tools, append the results, and loop back to the API.
Green means go. Keep the cycle alive. What's the red light?
The red light is end turn. This means the agent has completed its full response, it has all the data it needs, it's reasoned through the prompt, and it's finished.
So it's completely done.
Yeah, your action here is to terminate the loop. You extract the final text, hand it back to the user, and the conversation state is settled.
Okay, but what about edge cases? Like, what if our agent hits a wall? Say it's processing a massive document and we just run out of allocated space.
Right, that would be the max token state. It basically means the output was truncated because you hit your token limit.
So it's like a parking meter running out of time mid-sentence. It's not that the car broke down or ran out of gas. It's a hard artificial cutoff imposed from the outside.
That is exactly what it is. And because it's an artificial cutoff, you must handle this as an error state.
Ah, an error state.
Yeah, the response is fundamentally incomplete. You can't just pass that back to the user as a final answer. You either raise an exception, or your architecture needs to dynamically increase the limit and retry.
So let's put you, the listener, in the hot seat for a second. Think about a scenario you might see on the exam. Your code receives an API response. You parse the JSON, and you read a stop reason of end turn.
Okay, consider the implications of the red light.
Right. Based on what we just discussed, what is your immediate next action regarding the message history array?
What do you do with that array?
Well, you terminate the loop and extract the final text. But crucially, you do not append this final response to the message history right now.
No, you don't.
You are done. You just return the text to the caller. Appending an end turn response to your working array is a total waste of your context window because there's no immediate next API call to make.
Exactly. The active loop is finished. Any further manipulation of the array is outside the scope of that specific execution cycle. You only update the permanent storage later.
So stopping is the easy part. Red light, you stop. But let's dive into the complexity of the green light.
Yeah, the green light is where it gets tricky.
When that stop reason is too loose, how do we actually handle feeding those tools back into the model without breaking the entire conversational chain?
And this brings us to the mechanics of tool result appending. When stop reason equals too loose, the API requires incredible precision.
Precision is key.
Yes. Specifically, your messages array must grow by exactly 2 entries before you make the next API call.
Wait, exactly 2. No more, no less.
Exactly 2. There is a non-negotiable 4-step sequence to building those entries. First, you must append the full assistant response that you just received.
Okay, the full response.
You take the entire response content list and append it to your messages array as an assistant role message. And this includes all text blocks and all tool use blocks.
Hold on. Let me step into the shoes of a developer trying to optimize their architecture for a second.
Sure, put the hat on.
If the model just needs the raw data from my database to continue reasoning, why can't I just strip out all those bulky tool use blocks from the assistant's response?
I see where you're going with this.
Yeah, like couldn't I just append the text part of the assistant's response and save myself a bunch of context tokens?
It is so tempting, especially when you're trying to minimize latency and token costs, but it is completely destructive to the agent's memory.
Really? Completely destructive?
Yeah. If you strip the response down to text only, you are destroying the context Claude needs. Claude uses those specific tool use blocks to link the results you're about to provide back to its own internal reasoning.
Oh, I see.
If you delete them, you will cause silent reasoning failures. The model will essentially wake up on the next turn, see a bunch of random database records you provided, and forget why it asked for that data in the first place.
That's a nightmare. So never cherry-pick blocks to save a few tokens. Full response appended. Okay, so that's the first entry added.
Right, you must preserve every single block.
Now I need to build a second entry. I assume the next logical step is to iterate through that response, find the actual tool request, execute my local code, and then pass that data back.
That's step 2 and 3, yeah.
Yeah.
You extract the tool requests by filtering for anything where the block type is too loose.
It makes sense.
Then you run your local functions, whether that's querying a SQL database, hitting a weather API, searching the web, whatever. Then you build a result object to send back.
Okay.
And here's a massive red flag for the exam. Your tool use ID in the result must match the block ID from Claude's request character for character.
Character for character. No generating new ones.
Never modify it. Never generate a new one. And if your local tool returns a complex object, like a deeply nested dictionary, make sure you serialize it into a string format with JSON.dumps before sending it back.
Okay, match the ID exactly. Serialize complex objects. Got it. So I have my local results ready. If Claude asks for 3 different tools, I have 3 results. Do I just append them one by one as 3 new messages?
No, absolutely not. You append all of those tool results in one single user role message.
Wait, all of them?
Yes. Even if Claude called 5 different tools simultaneously, all 5 results get bundled together into an array, and that single array becomes the content of one new user message.
Let's think about why that is, because I know developers often trip up here. They write a script, and they append each individual tool result as its own separate user message.
It's a very common mistake.
Right, like one user message for the weather data, a second user message right after it for the stock data. If you do that, the API is going to throw a massive validation error. Why?
Because the Claude API enforces strict role alternation. User assistant, user assistant.
You cannot have a user message followed immediately by another user message. It violates the core structure of the conversation. I really want to latch onto this concept of strict role alternation.
It's fundamental.
Think of the API as a strict bouncer at an exclusive club. And this club has a mandatory alternating dress code for entry.
Okay, I like this.
You can have someone in a red shirt representing the user walk in. But the next person in line must be wearing a blue shirt, the assistant.
Right.
If 2 people in red shirts try to walk in back to back, the bouncer shuts the whole line down. Validation error.
But why does the bouncer care so much? It's not just arbitrary rulemaking.
No, it's not. It comes down to how large language models are fundamentally trained.
Good.
Claude is an autoregressive model trained on vast data sets of dialogue trees.
Okay.
It predicts the next token based on a very specific conversational rhythm. When you feed it a clean, alternating sequence of user and assistant, you're aligning with its foundational training.
Oh, that makes total sense.
If you break that pattern by shoving in 2 consecutive user messages, you corrupt the dialogue tree. The model loses track of who is speaking and whose turn it is to reason.
Wow.
Yeah, the API enforces this alternation to protect the model's cognitive state.
The bouncer isn't just being difficult, he's keeping the environment stable. To really visualize this bouncer enforcing the rules, let's look at an actual message state trace from a live run. Let's do it. Let's walk through one.
Let's say you ask an agent a multi-tool question, like, can you check the current weather in New York and also look up the weather in London?
A classic 2-city parallel execution task. Let's walk the array trace microscopically.
Okay.
At state 0, before we even make our first call to the API, how many entries are in our messages array?
Just one, right? The initial user message asking the question. A single person in a red shirt walking up to the door.
Exactly. We call the API. Claude evaluates the prompt and realizes it needs weather data for 2 different locations. It sends back a response with a stop reason of Toulouse.
Right.
What does state 1 look like after we do that first step of appending the full assistant response?
Well, now our array has 2 entries. We have the initial user message, and right behind it, we've appended the new assistant response.
All right.
And this assistant response contains a text block saying, I'll check the weather for both cities, and it also contains both tool use blocks. Let's call them ID Toulouse 01 for New York and ID Toulouse 02 for London. User, then assistant, the bouncer is happy.
Very happy. Now your application takes over. You execute both weather checks locally. You gather the data. How do we build state 2 to get ready to pass control back to Claude?
Okay, we bundle. We take the result for New York, making sure we attach that exact Toulouse 1 ID so Claude knows what it is.
Yes.
We take the result for London, attaching Toulouse 2. We put both of those results into a single list, and we append that list as one new user message.
That is exactly it.
So state 2, right before we call the API again, has exactly 3 entries. User, assistant, and the new bundled user.
3 entries total. The alternating sequence is perfectly maintained. The bouncer sees red, blue, red, and the IDs flawlessly mirror the requests.
This trace brings up an architectural formula you should absolutely memorize for the exam to predict your array sizes at any given point. It's 1 plus 2n.
Yeah, let's break that formula down for them.
Okay.
The 1 is your initial user prompt. The 2n represents the pair of entries added for every tool loop iteration, specifically the assistant's request and the user's bundled results.
Right, they always come in pairs.
Exactly. So if you have 1 tool calling iteration, n is 1. 1 plus 2 equals an array size of 3.
And if Claude got that weather data, but then decided it needed to call a third tool to check flight delays between those cities, it loops a second time, n becomes 2, your array size will be exactly 5 entries.
It scales predictably every single time. What is fascinating here is what happens at the very end of the trace, which connects back to our earlier point.
Oh, right.
On that final call, Claude has all the weather and flight data it needs. It formulates a final comparison, decides New York is warmer, and sets the stop reason to end turn.
Yep, the red light.
And as we established, that final response is never appended to the working array.
Right, because the formula dictates the state going into an API call. At end turn, there is no next call. The task is over. We extract the text, show the user, and the loop terminates.
Exactly. But, looking at all of this, managing these precise array sizes, tracking exact alphanumeric IDs, bundling everything into single turns to avoid validation errors.
That sounds like a headache.
Managing this manually in your own code sounds incredibly tedious.
It sounds like a great way to introduce a dozen tiny bugs, honestly. Can't the SDK just handle this heavy lifting for us?
Well, the Claude Agent SDK does offer an automatic loop feature. If you use it, the SDK manages the iteration behind the scenes.
Oh, nice.
Yeah, it handles the exact appending sequence we just traced out, and it dispatches the tool calls to your registered functions automatically. You essentially hand it your tools and let it run.
That sounds way easier.
It is. However, the certification exam specifically tests your ability to reason through the manual loop.
Of course it does. Meaning I have to own the while loop myself in the code. I have to write the logic that checks the stop reason and manages the array appending manually.
You own the architecture. Writing a manual loop is critical for debugging complex agent failures, for inserting custom routing logic mid-thought, and most importantly, for proving you actually understand the mechanics of autonomous flow.
So if I'm writing my own manual while loop, the biggest risk is creating an infinite loop, right? Like an agent that just talks to itself, calling tools endlessly, burning through API credits until my server crashes, which brings up a crucial production rule from our sources. The iteration cap.
Yes, any manual loop must implement an iteration cap. This is a hard limit in your code, something like setting a variable, while iterations is less than 50.
And this is a massive distinction that developers often miss. That iteration cap is purely a last resort safety net. It is a circuit breaker. It is not the light switch.
That's a great way to put it, and this raises an important question. Consider the architectural fallout when developers misunderstand this and use the iteration cap as the primary way to stop their loop.
Does that happen a lot?
It happens way more often than you'd think, and it leads to complete chaos in production.
Which brings us to the anti-pattern segment of our deep dive. The exam loves testing these common traps. We're going to walk through the 3 deadly sins of loop control.
Listen closely to these.
Yeah, because identifying why these fail in a live environment is the key to passing. Let's look at the first major trap. Natural language parsing.
This occurs when a developer writes a loop that extracts Claude's text response and searches it for specific keywords like task complete or final answer to decide if it should break the loop.
Why does this fail so catastrophically? Well, because natural language is fundamentally non-deterministic and fragile.
Exactly.
The model's phrasing changes with every minor version update or even a slight tweak to your system prompt. Today it says task complete. Tomorrow it updates its vocabulary and says, I have concluded the task.
And your code just misses it.
Your hard-coded keyword misses it, and your loop breaks. Plus, Claude might say, I'm done checking the weather in text, while simultaneously outputting a to-loose block to check the stock market in the same response.
Right.
If you just parse the text, you'd exit prematurely and abandon the stock check. Never parse text for control flow.
Never do it. Relying on text parsing completely ignores the deterministic signals the API provides. The second major trap is what we hinted at earlier, using the iteration cap as the primary stop.
Oh, this one is rough.
This looks like a developer writing a standard for loop, say, looping exactly 5 times and then returning whatever state they happen to be in, completely ignoring stop reason.
This one is insidious. Why does it fail? Because it silently truncates complex reasoning.
Silently truncates, yes.
Think of a scenario where an agent is investigating a complex cybersecurity threat. The task actually requires 7 distinct tool calls to cross-reference logs and find the right answer.
Okay.
If your arbitrary loop cap of 5 cuts it off early, the agent stops mid-thought. It forces the calling application to guess whether the agent actually finished its reasoning or if it just hit the wall and failed.
And you don't want to be guessing.
The safety cap should always be a while loop condition. And if that cap actually triggers, it must raise a severe runtime exception. Hitting the cap is an error state, not a successful conclusion.
A silent failure in an autonomous system is the worst kind of failure because you don't know the data is incomplete until it's too late. The final major trap is text content inspection. This is when a developer checks the last block in the array using a check like content-1.type equals text to decide if the agent is done talking.
Okay, I'm going to push back on this one.
Okay, let's hear it.
As someone building these systems, this kind of makes intuitive sense to me. If the last block in the array is a text block, doesn't that inherently mean Claude has stopped using tools, is done talking, and is giving me a final answer? Why is checking the last block an anti-pattern?
This is where the architecture gets incredibly nuanced, and it's a profound aha moment for a lot of developers. You have to account for features like extended thinking.
Ah, extended thinking.
When you enable extended thinking, Claude is doing massive internal reasoning before it outputs standard text or tools. It prepends a thinking block to the response.
Okay.
So a response where Claude ultimately wants to use a tool might look like this. A thinking block, followed by a text block where it talks to the user, followed by a tool use block. In that scenario, checking the last block works because it's a tool use.
Right. And a final end-turn response might look like a thinking block, followed by a text block. The last block is text. So far, my logic holds up.
But what happens if Claude decides to emit a thinking block, followed by a tool use block, followed by a text block?
Wait, can it do that?
Yes. It is perfectly valid for a model to emit conversational text after a tool call within the exact same turn, perhaps to explain to the user what tool it just triggered.
Oh, wow.
If your logic relies on position checking, if the very last block is text, you will assume the model is finished reasoning. In reality, the stop reason is still set to lose.
That is a trap.
By looking at the block order instead of the top-level variable, you will abandon pending tool calls and break the chain. Relying on block order is a fragile version-specific trap that will inevitably burn you.
Wow. The order of the blocks can change dynamically based on the model's reasoning style, its need to explain a tool call, or new features like extended thinking. You simply cannot trust the position of the blocks to tell you what state the loop is in.
You must always, always trust stop reason.
So what does this all mean when we zoom out? It boils down to a strict architectural separation of concerns. You use stop reason exclusively for your control flow to dictate whether the while loop continues or breaks.
Yes.
And you iterate over the content blocks purely for data extraction and tool execution, completely oblivious to what order those blocks arrived in. Control flow and data extraction are two totally separate, isolated systems in your code.
Exactly. If you intertwine them, your application will eventually break in production when the model's output structure evolves.
Take a deep breath. We have covered a massive amount of architectural ground today. You survived the deep dive into Domain 1. To bring it all home, let's summarize the ultimate cheat sheet you need to internalize.
Let's hear it.
First, stop reason is the one and only loop signal. Ignore the text, ignore the block order. Second, when appending tool results, maintain strict role alternation. All results go into exactly one user message, and the tool use ID must match the request identically.
Character for character.
And third, iteration caps are safety nets. If you hit the cap, you raise an exception. You do not silently return incomplete data.
If we connect this to the bigger picture, mastering these three mechanics is what separates a developer who just writes scripts to ping an API from a true AI architect.
That's a great point.
Anyone can send a prompt. But building a robust, autonomous system that never silently fails, never breaks conversational context, and scales elegantly, that requires a deep respect for the loop lifecycle.
You are transforming from someone who just asks the model questions into someone who builds the resilient environments where these agents actually live and work.
Before we wrap up, I want to leave you with a final puzzle to mull over, something that builds on everything we've discussed but looks toward the horizon.
Oh, love these.
As these models become increasingly multimodal, they are going to natively output entirely new block types. We aren't just going to see text or tool requests. We're going to see native audio streams or even real-time interactive UI components generated on the fly.
Oh, that's wild. Imagine a tool returning a fully functional interactive data dashboard instead of just a raw JSON string.
Exactly. If a tool returns an interactive graphic or an ongoing audio stream, how will the messages array evolve to maintain that strict user assistant rhythm?
That is tricky.
How does your manual loop capture and append that state when the output isn't static text or structured data anymore? It's a fascinating architectural challenge that the next generation of agentic systems will have to solve.
I love that. A little architectural homework to keep your brain working as you prepare for the exam. From our digital command center here, we want to thank you for joining us on this deep dive. Keep that stop reason in your sights, trust the traffic light over the bumper stickers, and good luck on your certification journey.